The first thing in the quarry is not a skeleton. It is a surface. A slope of pale rock under the sun, rough where wind has lifted the softer grains away, flat where a river once pressed sediment over sediment. Then, near the edge of the exposure, a shape appears that is too smooth to be ordinary stone. It curves out of the hillside like a fallen column. A single bone, not complete, not clean, but large enough that the people standing beside it look smaller than they should. It might be a femur. It might be part of a vertebra. At first, in the heat and dust, it may even seem like a piece of petrified wood. That has happened before. Some of the largest dinosaurs ever found first entered the modern world as strange lumps on ranch land, objects too big to make sense of until the rock around them began to come away. A brush passes over the surface. More bone appears. Then more. The hollow of a joint, the broken edge of a shaft, the grain of ancient tissue replaced by minerals, carrying the shape of an animal that once crossed a floodplain with the weight of a small house and the calm routine of a grazing animal. This is where the age of giants becomes real. Not in a painting, not in a museum mount, not in the word enormous, but in the difficulty of lifting one fossil from the ground. A thigh bone can be taller than a person. A neck vertebra can be wider than a chest. A rib can curve through the sediment like the frame of a boat. The animals that left these bones were sauropods, long-necked, long-tailed, four-legged dinosaurs that became the largest animals ever to walk on land. Some lived in the Jurassic, in forests of conifers, cycads, ginkgos, ferns, and horsetails. Others, the Titanosaurs, carried the same basic plan into the Cretaceous, across southern continents, river plains, coastal lowlands, and volcanic landscapes, where ash layers later helped preserve their remains. They were not simply big dinosaurs. They were the extreme edge of land animal life. Their bodies tested the strength of bone, the reach of blood, the efficiency of breathing, the growth of young animals, the productivity of forests, and the patience of ecosystems that had to feed them day after day. A single adult could weigh more than many elephants. A herd crossing wet ground could leave a trackway that hardened into stone, each footprint a basin pressed into mud by a living column of flesh and muscle. A tail could stretch behind the body for more than the length of a bus. A neck could move through the trees like a slow crane, not built for drama, but for feeding. If the age of giants is what brought you to Jurassical, subscribing keeps the next deep time journey within reach. The title of this world is often spoken through names: Diplodocus, Apatosaurus, Brachiosaurus, Camarasaurus, Mamenchisaurus, Argentinosaurus, Patagotitan, Dreadnoughtus, Alamosaurus. They sound like museum labels now, but each name began as something physical. A piece of bone in a cliff, a sequence of vertebrae in sandstone, a footprint on a bedding plane, an eggshell fragment weathering out of red sediment. The promise of those names is scale. But scale alone does not explain them. To understand sauropods and titanosaurs, it is not enough to say that they were huge. The question is how a land animal becomes that huge, how it eats enough, breathes enough, grows quickly enough, and carries itself across ground that was sometimes dry, sometimes flooded, and sometimes dangerous. Their story does not belong to one period only. It begins before the classic giants, in the Triassic, when the ancestors of sauropods were much smaller animals, moving through a world still dominated by other reptiles. It expands in the Jurassic, when long-necked herbivores became some of the central animals in many dinosaur ecosystems. It continues into the Cretaceous, when Titanosaurs became widespread and diverse, some modest in size, others among the greatest land animals known. The biggest of them are difficult animals to measure. Many are known from incomplete skeletons, some from a few enormous bones. Mass estimates can change when scientists use different methods, when missing parts are reconstructed more cautiously, or when the density of the living animal is reconsidered. The largest dinosaur is not a simple title. It is a debate built from fragments. Still, the broad shape of the answer is clear. No mammal on land ever reached their size. No elephant, no rhinoceros relative, no prehistoric herbivore of the Cenozoic matched the upper range of the largest sauropods. In the water, whales would go farther because the sea helps support mass. On land, gravity never stopped pulling, and sauropods still became giants. Imagine the ground before one of them arrives. A late Jurassic riverbank has dried just enough to hold shape. Ferns crowd the lower edge. Conifers stand behind them. A turtle slides into the water. Insects move through decaying wood. Somewhere beyond the trees, a theropod is following the scent of a carcass. Then the first foot enters the mud. Broad, rounded, heavy. The toes are not spread like a bird's. The front foot is more like a padded column. The hind foot leaves a larger mark, sometimes with claw impressions along its front edge. The animal does not hurry. Its body passes over the bank, and the mud records what the eye would have struggled to believe. Trackways can preserve what bones cannot. A skeleton shows structure after death. A footprint shows weight in motion. It tells us how the animal stood, how wide its gait was, whether the feet turned inward or outward, how groups may have moved across a landscape. Some sauropod trackways suggest animals traveling in the same direction, sometimes with juveniles separated from adults, sometimes with mixed groups. No single trackway proves a full social life. The fossil record rarely gives that kind of certainty. But when a bedding plane carries one print after another, when parallel paths cross the same ancient surface, it becomes hard to imagine these animals only as isolated giants drifting through empty forests. Sauropods were part of communities. They shared floodplains with smaller herbivores, armored dinosaurs, early birds in some later Jurassic settings, pterosaurs overhead, crocodile-line reptiles near water, turtles, fish, amphibians, insects, and predators that understood the difference between a young sauropod and a full-grown adult. That difference mattered. A hatchling sauropod was not born gigantic. It emerged from an egg that, even in the largest known titanosaurs, was far smaller than the body of the adult would suggest. The young had to grow through vulnerable stages, crossing from something a predator could swallow or tear apart into something that could survive by size alone. In that gap between egg and giant, the whole life of a sauropod was at risk. The nests, the eggshells, the tiny bones, the growth rings inside larger bones, all carry traces of a journey that began small and ended, for the lucky ones, almost beyond comparison. The body plan looks simple from a distance. 4 legs, long neck, long tail, small head, massive trunk. But each of those parts matters. The small head made the long neck possible. A heavy skull packed with large chewing teeth and powerful jaw muscles would have turned the neck into a burden. Sauropods avoided that problem by keeping the head light. They did not chew like horses or elephants. Their teeth cropped, stripped, raked, or clipped vegetation, depending on the species. But the real processing happened later, inside a large digestive system. Food entered the mouth, was swallowed quickly, and then spent time in a gut where microbial fermentation could break down tough plant matter. This is one of the reasons their bodies could become so large. A big digestive chamber is useful when the diet is fibrous and difficult. It allows food to remain inside long enough for bacteria to extract energy from leaves, conifer needles, fern fronds, and other Mesozoic vegetation. A large animal can carry that system more easily than a small one. Scientists still debate the details. The old idea that sauropods relied heavily on stomach stones or gastroliths as grinding tools is treated more cautiously now than it once was. Some stones found with dinosaurs may have been swallowed, but they do not necessarily prove a bird-like gizzard powerful enough to grind all food. The evidence has to be read carefully. What remains likely is that sauropods were high-volume feeders. They did not need delicate meals. They needed landscapes that could supply constant plant material. Their feeding was probably more like harvesting than browsing in the mammalian sense. The neck reached, the mouth cropped, the body moved on. A long neck changes the mathematics of feeding. An animal can stand in one place and cover a wide arc of vegetation without moving the whole body. It can reach high branches, low shrubs, or lateral patches depending on posture and species. The energy saved by not taking many steps becomes important when each step belongs to an animal weighing tens of tons. But no single posture fits all sauropods. Brachiosaurids had front limbs longer than their hind limbs, lifting the shoulders high and giving the body an upward slope. Diplodocids had longer tails and more horizontal bodies, with necks that may have swept through lower or middle vegetation. Mamenchisaurids evolved extraordinary neck length in their own direction. Titanosaurs varied widely. The long neck was not one solution. It was a toolkit. Different sauropods used it in different ways, reducing competition in ecosystems where several giants lived together. In the Morrison Formation of western North America, Apatosaurus, Diplodocus, Camarasaurus, Barosaurus, and Brachiosaurus were not all doing exactly the same thing in exactly the same places. Teeth help show this. Diplodocids often had narrow, peg-like teeth concentrated toward the front of the jaws, suited for stripping or cropping in a particular way. Camarasaurus had broader, stronger teeth, suggesting a different feeding style. Wear patterns, tooth replacement rates, skull shape, and jaw mechanics all point toward niche differences among animals that might look similar to the casual eye. Stand in front of a mounted Diplodocus and a mounted Camarasaurus, and the difference becomes more than academic. One has a long, low elegance, a skull that seems almost too small for the body. The other looks deeper, sturdier, with a more robust head and a body built for a different relationship with the forest. The giants did not need to be identical. In fact, they could not be. An ecosystem with multiple enormous herbivores requires partitioning. Some animals may feed higher, some lower, some in wetter floodplain forests, some in more open ground, some on softer plants, some on tougher material. The landscape had to be divided by behavior, anatomy, and opportunity. Beneath all of it, the skeleton carried the load. Sauropod legs were not long, springy limbs like those of a running horse. They were columns, set under the body, supporting weight with a directness that made sense for animals this large. The feet were padded, the joints massive, the limb bones thick, but not crude. The engineering is often hidden by the word massive. A sauropod femur is not simply a heavy pole. Its internal structure, muscle scars, joint surfaces, and growth tissues record a living organ shaped by stress. It had to resist bending. It had to support movement. It had to grow quickly without failing under its own increasing load. Bone histology, the microscopic study of fossil bone tissue, has shown that many sauropods grew rapidly. Their bones contain patterns of vascularized tissue associated with fast growth, interrupted in some cases by lines that record slower periods. A giant body did not appear overnight, but it may have reached large size faster than a mammal of comparable mass could. Rapid growth would have been a defense. The smaller an animal remained, the longer it stayed vulnerable. A young sauropod that could gain size quickly had a better chance of entering the zone where most predators could no longer treat it as easy prey. Growth was not only development, it was survival. The respiratory system may have been just as important. Sauropod vertebrae often contain internal spaces and external openings that show the presence of air sacs connected to the breathing system. These features are related to the system seen in birds, the living dinosaurs, where air sacs help move air efficiently through rigid lungs. Air-filled bones made the skeleton lighter than solid bone would have been. This mattered especially in the neck and trunk. A long neck built from dense, heavy vertebrae would have been much harder to support. Pneumaticity allowed large bones to be strong in the right places, while containing space where solid tissue was not needed. Some sauropod vertebrae look less like simple bones and more like natural architecture. Struts, chambers, walls, hollows. The bone is there where stress demands it, and absent where air can replace it. Fossils that seem heavy in the hand once helped carry bodies by being partly empty. This does not make sauropods light animals. A titanosaur estimated at 50 or 60 tons was still 50 or 60 tons. But it means the animal was not built like a solid stone sculpture. It was a living structure of muscle, air, blood, bone, gut, tendon, skin, and motion, all arranged around the problem of being huge on land. Blood pressure in long-necked sauropods has often been imagined as an almost impossible challenge. If an animal held its head far above the heart for long periods, the cardiovascular system would need to deliver blood upward against gravity. Some species may have avoided the most extreme demands by holding the neck lower much of the time. Others may have had special physiological solutions we cannot directly observe. The fossil record gives bone more readily than soft tissue. Hearts, lungs, blood vessels, and muscles vanish except in rare traces or indirect clues. So the living sauropod must be reconstructed with caution. The bones tell us what was possible, but not every detail of how it felt to breathe, feed, or lift the head. Still, the bones are enough to say that it worked. For more than 100 million years, in many lineages and many landscapes, long-necked dinosaurs solved the problem of size again and again. Before the largest sauropods appeared, there were smaller ancestors moving through a Triassic world that did not yet belong to dinosaurs. These early sauropodomorphs were often long-necked compared with their neighbors, but many still walked partly or mostly on two legs. They were not yet the great four-legged columns of the Jurassic. They were experiments in reach, feeding, and body size. Brachiosaurus from late Triassic Europe is one of the familiar early forms. It could grow large for its time, but it was not a sauropod giant in the later sense. Its forelimbs were not built like those of Diplodocus or Apatosaurus. Its body still carried the history of smaller, more agile animals. Yet the direction was visible. A longer neck, a larger gut, a herbivorous life expanding in scale. The Triassic ended with a catastrophe, and the world that followed opened ecological space for dinosaurs. The extinction at the Triassic-Jurassic boundary removed many competing lineages and reshaped land ecosystems. Dinosaurs did not win because they were destined to rule. They survived, and then they diversified in a damaged world where old roles had become empty. In the early Jurassic, those opportunities mattered. River systems crossed warm landscapes. Coastal plains spread beside shallow seas. Volcanic ash settled into basins. The first true sauropods and their close relatives began to explore the shape that would define them, shifting fully toward four-legged support, increasing body size, and lengthening the neck while keeping the head small. These early giants were not yet the biggest animals in the story. Some were large enough to dominate their local landscapes, but the upper limits had not been reached. Their importance lies in transition. They show the moment when a group of plant-eating dinosaurs moved from being large by Triassic standards to becoming something different, something the land had never carried before.
A fossil limb from this interval does not always announce the future at first glance. It may be a partial humerus, a vertebra with broken processes, a worn tooth, a pelvis distorted by pressure. But when enough pieces are compared across places and time, the pattern appears. The body is becoming more columnar. The torso is expanding. The neck is no longer a small extension of the head. It is becoming the instrument of the whole animal. The earliest sauropods also remind us that gigantism was not a single jump. Evolution moved through intermediates. Some animals retained primitive traits. Others carried features that would become standard later. The lineage did not know where it was going. No animal evolves toward a museum hall. It survives immediate conditions, one generation at a time.
Titanosaurus from Thailand, sometimes discussed as one of the earliest known sauropods, shows how complex this early record can be. Fossils are fragmentary, dates can be debated, and the early history of the group is still revised as new material appears. The beginning of sauropod gigantism is not a clean line on a chart. By the Middle Jurassic, the picture becomes clearer. Sauropods were widespread, and several lineages were becoming large in different regions. The continents were no longer arranged as they had been in the Triassic. Pangaea was breaking apart. Seas opened, climates shifted, and populations became separated by geography. Isolation gave evolution room to vary the sauropod plan. This is one reason the age of giants was not the same everywhere. A sauropod community in what is now North America was not identical to one in Africa, China, Europe, or South America. The plants, rivers, shorelines, seasonal patterns, and predators differed. The sauropods differed with them. In China, long-necked forms such as Mamenchosaurids pushed cervical length to extraordinary proportions. Some species had necks that made up nearly half of the total body length. Their vertebrae were elongated and complex, built around the same need to reduce weight while maintaining strength. A neck that long was not an ornament. It was a feeding system stretched to its farthest visible reach. To imagine one alive is to imagine a body partly hidden behind trees while the head moves far away from the shoulders, passing through conifer branches with slow precision. The animal does not need to run. It does not need to rear up like a creature in an old painting. Its advantage is reach, patience, and the volume of a body that can turn poor food into life. Other sauropods took different paths. Diplodocids, later famous from the late Jurassic, became long, low, and tail-heavy, their bodies balanced between an extended neck and an even longer tail. Macronarians, the broader group that includes Camarasaurus and Brachiosaurids, often had more robust skulls and different feeding mechanics. Titanosauriforms began building the foundation for later Cretaceous success. The names can become technical quickly, but the point is straightforward. Sauropods were not one animal copied across time. They were a radiation, a branching spread of forms, all recognizable as long-necked giants, but each shaped by its own ancestry and environment. The late Jurassic gives us some of the most familiar scenes. Western North America, especially the Morrison Formation, has preserved a world of river channels, floodplains, droughts, floods, volcanic ash, and bones. Here, the giants are not just isolated discoveries. They are part of an entire ecosystem, repeated across quarries and rock layers. The Morrison landscape was not a single endless forest. It included river corridors, open floodplains, ponds, lakes, wet intervals, dry intervals, and patches of vegetation that shifted with climate and sediment. Ferns, cycads, ginkgos, horsetails, and tall conifers formed the plant world. There were no grasses in the modern sense, no flowering meadows, no fruiting trees like those familiar today. Apatosaurus moved through that world with a heavy, deep body and powerful limbs. Diplodocus stretched longer and more lightly, at least compared with Apatosaurus, its whip-like tail trailing behind. Camarasaurus appears often in Morrison deposits, shorter-necked than Diplodocus, more compact, with a skull that suggests different feeding. Brachiosaurus was rarer, taller at the shoulder, with forelimbs that lifted its front body high. The quarry wall at Dinosaur National Monument shows how such animals entered the fossil record. Bones accumulated in river sediment. Some were moved by water before burial. Some were disarticulated, separated from the bodies they once formed. Others bear marks from scavenging. The wall is not a peaceful herd frozen in a single moment. It is a record of death, transport, burial, and preservation. That is often how the age of giants reaches us. Not as perfect scenes, but as deposits. A river carries bones. A drought concentrates animals near water. A flood buries remains quickly enough to protect them from complete destruction. Minerals seep into pores. Time turns sediment into rock. Erosion later opens the layer to the air. A visitor sees a bone. The scientist sees a process. The animal itself is somewhere between them, gone from life, present in structure, waiting to be understood through the damage and accidents that preserved it. In Tanzania, the Tendaguru beds preserve another famous late Jurassic assemblage. There, a giant brachiosaurid, known for many years as Brachiosaurus branchi, and now often called Giraffe Titan, reveals how similar body plans appeared on different continents. Its skeleton has shaped public imagination for generations, especially through museum mounts where the neck rises high above the floor. Giraffe Titan was not the biggest sauropod ever, but it was enormous and historically important. Its proportions show a high-browsing form, with long forelimbs and a body that angled upward toward the shoulders. Standing beside its mounted skeleton, a person can see why early 20th century scientists and museum visitors struggled to find ordinary language for such animals. The late Jurassic was also a time of predators. Allosaurus is the familiar name from the Morrison, a large theropod with serrated teeth and a skull built for cutting flesh. Ceratosaurus and Torvosaurus shared parts of the same broader world. These animals did not spend their lives dramatically attacking healthy adult sauropods. More often, the vulnerable targets would have been juveniles, the injured, the trapped, the dead. A full-grown sauropod was dangerous by existing. A misplaced foot could crush, a tail could strike. The mass of the body made any close approach risky. Predators evolved in the presence of giants, but the giants were not helpless mountains of meat. They were living animals with senses, movement, group behavior in some cases, and the simple protection of scale. Bite marks on bones can show contact between predator and prey, but they do not always reveal whether the bite happened during a hunt or after death. A tooth groove on a sauropod bone may record scavenging at a carcass as easily as predation on a living animal. Paleontology often begins with evidence and ends with several possible stories, not just one. This caution matters because sauropods are easy to turn into spectacle. Their size invites exaggeration. Their predators invite scenes of attack. But the daily life of a sauropod was probably less cinematic than the moment of danger. Most of its time was spent feeding, moving, resting, digesting, avoiding bad ground, following water and vegetation, and growing if it was young. A giant herbivore is not defined by battle. It is defined by appetite. Every day, the animal had to take in enough plant matter to keep its body alive. It had to regulate heat. It had to maintain balance. It had to lift and place its feet carefully. It had to move through a landscape that changed with seasons and floods. Picture a morning after rain. The floodplain is damp, and shallow pools reflect a pale sky. Ferns are bent under water droplets. The trunks of conifers stand dark against low mist. A herd, if that is what it is, passes slowly along the higher ground. The smallest animals remain near the edges where movement is easier, while the adults occupy the open track ahead. The sound would not be constant roaring. There may have been low calls, breath, footfalls, branches tearing, mud releasing under weight, insects in the wet vegetation, water shifting as a tail or leg passed near a bank. The scale would be immense, but the rhythm could be slow. We often imagine giants as exceptions to nature. In their own time, they were ordinary members of their ecosystems. Extraordinary to us, familiar to the animals around them. A turtle in a Jurassic pond did not know it lived beside a record breaker. A pterosaur crossing above the trees did not see a museum icon. It saw a large herbivore moving through the same weather. The age of giants, then, was not a single age of maximum size. It was a long experiment in how ecosystems can support immense herbivores. The experiment began in smaller bodies, grew through the Jurassic, and continued after many classic Jurassic forms disappeared. By the end of the Jurassic, the sauropod story was not ending. It was changing. Some lineages declined in certain regions, others continued. Titanosauriform sauropods, especially the lineage that would lead to Titanosaurs, were already positioned for a much larger role in the Cretaceous. The giants of the next period would not simply repeat the giants of the last one. The Cretaceous brought new coastlines, new plant communities, new predator groups, and a world in which flowering plants began to spread. Grasslands had not yet become the dominant open habitats of the later Cenozoic, but the plant world was changing. Angiosperms entered ecosystems that had long been organized around conifers, cycads, ferns, ginkgos, and other older lineages. Sauropods did not vanish when flowering plants appeared. That older story is too simple. In many southern continents, titanosaurs flourished during the Cretaceous, living alongside evolving angiosperms while still feeding on a variety of plant resources. Their success shows that the age of giants adapted rather than simply fading. In South America, especially Patagonia, the Cretaceous record produced some of the most remarkable giant bones ever found. Vast floodplain deposits, ash layers, and river sediments preserved pieces of animals so large that even a single vertebra could change the conversation about maximum body size. The giants of Patagonia are often known from incompleteness and abundance at the same time. One animal may be fragmentary, another may be represented by many bones from several individuals. A quarry may contain enough material to build confidence in proportions, while another famous species may rest on far fewer pieces, each so huge that it cannot be ignored. Argentinosaurus is one of those animals whose name has become almost inseparable from size. Its fossils come from the Huincul Formation of Argentina, a Cretaceous world of rivers, floodplains, and large dinosaurs. The remains are incomplete, but the bones that are known are enormous. A dorsal vertebra rising more than a person can easily imagine. Limb material that suggests an animal in the upper range of terrestrial life. Because Argentinosaurus is fragmentary, its mass is not a fixed number. Estimates have varied, sometimes widely. Many modern discussions place it somewhere around the range of 60 to 75 tons, though different models produce different values. The honest answer is not a single clean figure, but a cautious range built from partial evidence. That uncertainty does not make the animal less real. It makes the science more honest. The bone is real. The formation is real. The scale is real. What changes is the reconstruction placed around the surviving material, the body volume inferred, the assumptions about soft tissue, and the method used to convert dimensions into mass. Patagotitan offers a different kind of evidence. Its fossils were discovered in Patagonia after a ranch worker noticed a huge bone weathering from the ground. Excavations later produced hundreds of bones from at least 6 individuals. That amount of material gives scientists a stronger basis for reconstructing the animal than they have for some other giant titanosaurs. Patagotitan was still not complete in the way a small animal might be complete. Sauropod skeletons rarely are, but compared with many giant candidates, it is generous. Femora, vertebrae, limb bones, and other elements made it possible to estimate a body length of more than 30 meters and a mass in the many tens of tons, with published ranges depending on method. The quarry itself tells a story beyond the animal's body. Several individuals seem to have been buried in separate flood events. That means the site is not just a death scene. It is a place where a landscape repeatedly trapped, transported, or covered giant animals. The bones point not only to size, but to floodplain behavior, sediment, water, and recurring conditions.
A living Patagotitan would not have been a museum silhouette. It would have been an animal moving through Cretaceous Patagonia, feeding on plants available in that environment, carrying a long neck above a deep body, placing enormous feet in soil that could harden, crack, flood, and vanish under new sediment. Dreadnoughtus, from southern Patagonia, entered public attention because of the completeness of its skeleton compared with many other giant titanosaurs. Its name means fearing nothing, and the name fits the adult image, though the individual preserved was likely not fully grown. It includes important limb bones that allow body mass estimates from circumference, but its mass has also been debated. Initial estimates put Dreadnoughtus extremely high, near 60 tons. Later volumetric studies argued for lower values, showing how sensitive giant dinosaur masses are to reconstruction. A few centimeters of width across a body outline, a different assumption about density, or the shape of missing soft tissue can shift the final number by many tons. That may seem frustrating if the goal is a simple ranking, but in paleontology, uncertainty is often the most interesting part of the evidence. It reminds us that a fossil is not a complete animal waiting only to be named. It is a limited survival from a vanished body, and science has to rebuild the missing parts without pretending they were preserved. The largest titanosaurs were not alone. South America also held other enormous forms, such as Futuloncosaurus, Puertosaurus, Notocolossus, and several more whose remains contribute to a picture of repeated gigantism. Some are known from relatively limited material, others from more informative skeletons. Together, they show that immense body size evolved more than once within titanosaurs. This repeated emergence matters. It means the upper range of size was not a freak accident confined to one animal. Several lineages approached extraordinary dimensions.
The Cretaceous landscapes of Gondwana, especially in South America, seem to have supported a recurring push toward giant bodies. But titanosaurs were not all giants. Some were much smaller. Saltosaurus from Argentina was modest compared with Patagotitan or Argentinosaurus, and carried bony armor in the skin called osteoderms. This is an important correction. Titanosaur does not mean colossal by default. It means a member of a diverse sauropod group that ranged from medium-sized animals to record contenders. Titanosaurs became the last great sauropod radiation. They spread widely, with fossils known from South America, Africa, Europe, Asia, North America, Australia, and Antarctica. They lived until the end of the Cretaceous, meaning that long-necked giants were still present when the asteroid struck near what is now the Yucatan Peninsula. In North America, Alamosaurus represents one of the last sauropods of the continent. It lived in the late Cretaceous of the American Southwest, in landscapes very different from the Jurassic Morrison floodplains. Its fossils show that sauropods returned to or persisted in North America after a long interval in which their record there was sparse. The Cretaceous record can be uneven. Absence in the rocks does not always mean absence in life. Sediments may not preserve the right habitats. Fossils may not have been found yet. Geological time is sampled irregularly, and the history of sauropods on any continent has to be read with that incompleteness in mind. Still, titanosaurs clearly changed the final chapters of sauropod history. Their bodies often differed from classic Jurassic forms. Many had wider stances, with limb posture that placed the feet somewhat farther from the midline. Their tails, vertebrae, limb proportions, and skulls varied in ways that made them more than just late copies of Diplodocus or Brachiosaurus.
Their teeth also often tell a story of specialized feeding. Many titanosaurs had narrow, pencil-like teeth, usually replaced rapidly. These teeth were not built for chewing. They were cropping tools, part of the same high-volume feeding strategy that had served sauropods for so long. In some fossil beds, isolated titanosaur teeth are more common than skull material. Skulls are rare in many sauropods because they were lightly built, loosely attached compared with the massive postcranial skeleton, and less likely to preserve. A missing skull can make a giant harder to understand because feeding begins at the mouth. Sometimes the skull does survive. Rapidosaurus from Madagascar, a late Cretaceous titanosaur, is important because it is known from skull material along with parts of the skeleton. It helps fill a gap in our understanding of titanosaur heads, showing the living front end of animals too often reconstructed from necks, backs, hips, and limbs. A sauropod head could seem almost delicate compared with the body behind it. The nostrils, jaw bones, teeth, and eye sockets belong to an animal that had to sense its environment, choose food, watch for danger, and interact with others. The smallness of the skull should not make it seem insignificant. It was the point where the giant met the world. In a museum, the skull is often the part a child looks for first. The teeth answer the simple question of what it ate. The eye socket makes the animal feel present. The neck and body provide scale, but the head provides a face. For many sauropods, that face is reconstructed from relatives. The missing pieces are filled in with comparison and caution. This is why a mounted giant can look more complete than the evidence that created it. Museums must show an animal, but the science behind the mount is sometimes a conversation between preserved bone and educated inference. The largest sauropods also changed how paleontologists work in the field. A small fossil can be wrapped in plaster and carried by one person. A giant vertebra may require a crew, cranes, vehicles, roads, funding, time, and careful planning. The work is physical before it is theoretical.
Digging a titanosaur out of rock is a negotiation with weight. The fossil is heavy. The jacket protecting it becomes heavier. The surrounding sediment may be unstable. Weather can interrupt work. A bone that survived 90 million years can still be damaged by a careless tool, a bad lift, or a sudden storm. This physical effort shapes the fossil record in quiet ways. Large bones may be noticed more easily because they weather from hillsides as strange shapes, but they are also difficult to collect completely. Some are left in the ground for years. Some are lost to erosion before anyone reaches them. Some break during excavation. The giants make themselves visible and difficult at the same time. Once in a museum or laboratory, the preparation continues. Rock is removed slowly. Glue stabilizes cracks. Measurements are taken. Surfaces are scanned. Comparisons begin with other fossils around the world. A single bone can pass from field jacket to lab bench to paper to public display, gathering meaning at each stage. The public often meets the giant only at the end, after the dust, plaster, shipping crates, preparation needles, and spreadsheets. By then, the animal has become a name and a silhouette. But the real story began with a weathered edge in the ground, and someone noticing that the stone had the wrong shape. The scientific story of giant sauropods has also changed across generations. Early reconstructions often placed the largest forms in water, as if their bodies were too heavy for land. Brachiosaurus and other giants were once imagined standing in lakes, their nostrils high, using water to support mass. That image has largely been abandoned. Sauropods were land animals. Their limbs, trackways, bone structure, and sedimentary contexts show animals walking on terrestrial surfaces. They may have crossed water, fed near rivers, or moved through wetlands, but they were not helpless swamp dwellers. Their bodies were capable of supporting themselves on land because they evolved to do exactly that. This change in interpretation is important. It shows how dinosaurs are not fixed ideas. They are revised animals. Each generation inherits old images, tests them against new evidence, and sometimes lets them go. The giants have moved from sluggish swamp monsters to active terrestrial herbivores with complex biology. That revision makes them more impressive, not less. A creature held up by water is one kind of marvel. A creature carrying 50 tons across a dry floodplain, breathing through air sacs, growing fast, feeding high, and leaving footprints in mud is another. The age of giants was built on land under the full demand of gravity. That is the central fact. Every sauropod bone, from a cervical vertebra to a toe bone, belongs to a body that had to stand. Standing begins at the feet. Sauropod front feet were usually arranged like vertical supports, with the weight passing through a compact hand. The hind feet were broader and more recognizable, with claws on some toes. Trackways show this difference clearly. Smaller, crescent-like or rounded front impressions, larger hind impressions behind or partly over-printing them. A footprint is anatomy pressed into sediment. It preserves the underside of movement, not the museum skeleton. In some tracks, the front feet appear almost horseshoe-shaped. In others, soft tissue pads expand the print beyond what bones alone would suggest. The living foot was not a dry arrangement of bones. It had flesh, cartilage, skin, and weight. When a sauropod crossed mud, the print could deform under pressure. Sediment might rise around the edges, water might seep in. A later step could crush the earlier shape. If buried soon after, the surface could harden into a record of motion. If exposed too long, rain and sun would erase it before stone could remember. The best trackways are rare for that reason. They require the right mud, the right depth, the right timing, and the right burial. Too wet and the print collapses. Too dry and the foot barely leaves an impression. Too much erosion and the surface is gone. Fossil footprints are not simply left. They survive a series of narrow chances. Where they do survive, they let us see behavior in a way bones cannot. Some trackways are narrow gauge, with the feet close to the midline, often associated with certain sauropod groups. Others are wide gauge, with left and right prints farther apart, a pattern common among titanosaurs. The stance of the living animal appears in the geometry of its path. A wide stance may have helped some titanosaurs support broad bodies or move with different limb mechanics. It also gives trackways a particular look, as if the animal carried its mass with a wider base. The shift is one of the subtle ways titanosaurs differed from many earlier sauropods. The tail is another major part of the body that is easy to overlook. In diplodocids, the tail could be extraordinarily long, tapering to slender vertebrae near the end. It balanced the neck and trunk, contributed to movement, and may have played roles in communication or defense. Claims that tails cracked like whips remain debated, but the anatomy shows they were not passive ropes. For a giant animal, balance matters constantly. Neck, trunk, hips, tail, and limbs form one system. Change the neck, and the tail matters. Change the stance, and the hips matter. Change the body depth, and the limbs respond. Sauropods were not assembled from spectacular parts. They were integrated animals. Soft tissues are harder to reconstruct. Skin impressions from sauropods and titanosaurs are known in some cases, showing scales rather than fur or feathers. The scales could vary in size and arrangement across the body. Osteoderms in some titanosaurs add another layer of complexity, with bony elements embedded in the skin. Saltosaurus is the classic example of a titanosaur with armor. Its osteoderms were not like the full body armor of ankylosaurs, but they showed that at least some sauropods carried dermal bone. The function may have included defense, mineral storage, display, or several roles at once. As usual, biology does not need to choose only one purpose.
Armor on a sauropod changes the way we imagine vulnerability. Even a medium-sized titanosaur was not a soft target. Skin, muscle, mass, tail, herd behavior, and sometimes osteoderms all stood between a predator and a meal. The predator still had opportunities, but the herbivore was never just waiting to be taken. Heat is another problem for giants. Large animals lose heat more slowly than small ones. This can be useful in stable conditions, but dangerous in warm climates. A sauropod standing in the sun carried a volume of living tissue that generated metabolic heat and shed it only through the surface of the body, breath, blood flow, and behavior. Paleontologists do not have a sauropod thermometer. They infer from body size, growth, bone tissue, respiratory anatomy, climate, and comparison with living animals. The old categories of cold-blooded and warm-blooded are too simple for dinosaurs. Sauropods likely had metabolic lives unlike those of any living animal of similar size, because no living land animal is similar in size. Gigantothermy may have helped stabilize body temperature. A large body changes temperature slowly, buffering daily fluctuations. But if heat builds too much, the same stability becomes a risk. Shade, water, activity patterns, blood flow, and respiratory surfaces may all have played roles in managing temperature. A giant at noon may have behaved differently from a giant at dawn. It might feed more actively in cooler hours, stand in shade when available, move toward water, or reduce activity during the hottest part of the day. These are reasonable possibilities, not scenes preserved directly. The bones open the question. Living animals help us imagine possible answers. Growth adds another layer. A sauropod hatchling and an adult did not experience the same world. The hatchling lost heat quickly, hid more easily, and faced many predators. The adult retained heat, moved with authority, and may have had little to fear from most carnivores. One species contained several ecological stages across its lifetime. A nest site brings that contrast into focus. The eggs are not monstrous. They are round or slightly oval, sometimes around the size of a large ball, with shells thin enough for an embryo to break. Around them, in the sediment, are traces of a parent body that may have been tens of thousands of times heavier than the life inside each shell. Mahuevo in Patagonia is one of the most important titanosaur nesting localities. It preserves eggs, eggshell, nesting horizons, and even embryonic remains with skin impressions in some cases. The site gives rare evidence of reproduction in animals whose adult skeletons can otherwise dominate the story. The nests suggest colonial nesting behavior, or at least repeated use of nesting grounds by many individuals. Eggs were laid in shallow depressions or buried in sediment and vegetation in some interpretations. The details vary by site and remain studied, but the broad message is clear. Giant sauropods began life in places that could be preserved at the scale of eggshell. Eggshell is a fragile witness. It breaks, scatters, weathers, and can be difficult to assign. But under magnification, shell structure reveals patterns. Thickness, pores, ornamentation, and microstructure can connect fragments to dinosaur groups. A handful of broken shell can tell us that a nesting ground once existed where nothing alive remains. The reproductive strategy of sauropods probably differed from that of large mammals. Elephants produce one calf after a long gestation and invest heavily in parental care. Sauropods laid eggs, likely many over a lifetime. Their young may have grown quickly and faced high mortality. The path to being a giant may have depended on producing enough young that some survived the dangerous early years. Whether adult sauropods guarded nests closely is uncertain. The fossil evidence does not show sauropod parenting with the clarity sometimes seen in certain theropod or ornithischian sites. A titanosaur adult was also so large that direct brooding over eggs would be difficult or impossible in the way a bird sits on a nest. This does not mean they were careless.
It means their reproductive behavior was probably different. They may have chosen nesting grounds carefully, used warm sediment, vegetation, or geothermal conditions in some places, and returned to favorable sites. Nest choice itself can be a form of parental investment. At some localities, repeated nesting layers suggest that dinosaurs came back to the same region over time. The landscape mattered. A suitable nesting ground needed sediment that could hold eggs, moisture levels that would not drown or dry them, temperature conditions that allowed embryos to develop, and enough distance from constant disturbance. Imagine a Cretaceous floodplain during nesting season. The adults move across open ground, immense and deliberate. Behind them remain shallow, disturbed patches, buried eggs, broken vegetation, prints pressed into damp sediment. Weeks or months later, the surface changes again. Rain falls, mud shifts. Some eggs hatch, some do not. A flood arrives and writes the scene into geology. The young that emerged were proportionally different from adults. Their bones, limbs, and skulls changed as they grew. A juvenile sauropod may have fed on different plants or occupied different microhabitats than an adult. It could move through denser vegetation, hide in places inaccessible to giants, and face a predator world scaled to its own body. This life stage separation may help explain some fossil patterns. Trackways sometimes suggest groups of similarly sized juveniles moving together, or pathways where adults and young are separated. Bone beds may preserve certain age classes more often than others. These patterns are debated, but they raise a simple point. Sauropod societies, if we can call them that, may have been structured by size. An adult herd moving with hatchlings would face practical problems. The stride length, speed, feeding height, and vulnerability of the young differed too greatly. Juveniles may have formed their own groups or remained in safer habitats until they reached larger sizes. The fossil record gives hints, not a complete family portrait. Predators would have understood the difference. A hatchling titanosaur was food from many animals. A juvenile might draw the attention of medium-sized theropods, crocodiliforms near water, or opportunistic hunters. A subadult nearing several tons became harder to attack. The adult, standing at full height, entered a category where danger shifted toward disease, injury, drought, and accident. Accident may have killed many giants. A deep mud trap, a riverbank collapse, a drought that forced animals toward shrinking water, a flood that caught a weakened individual. The fossil record of large herbivores often involves landscapes where water gathers bodies and sediment quickly covers them. A giant can die from something small. A bad step, an infected wound, a dry season that lasts too long. The scale of the body does not remove fragility. It only changes the terms. When a sauropod died, the body became a landscape for other organisms. Predators and scavengers opened the hide. Smaller animals fed between ribs. Insects entered soft tissue. Bacteria worked through the body. Bones separated as ligaments decayed. A flood could scatter the skeleton. A quiet burial could preserve more of it. The path from carcass to fossil is never guaranteed. Most giants vanished completely. Their bones weathered, dissolved, broke, or remained buried beyond discovery. The famous skeletons are exceptions, not the normal fate. For every Patagotitan bone collected, countless other sauropods left no trace we will ever find. This incompleteness is why the record of giant sauropods is both spectacular and frustrating. The animals most able to impress us are often known from the least complete evidence. Their bones were enormous, but complete preservation of an enormous body required an unlikely chain of events. The missing parts invite imagination, but also restraint. A vertebra can imply a body. A femur can imply weight. A track can imply movement. None of them gives permission to invent without limit.
The best reconstructions keep one hand on the evidence, even when the animal itself is almost too large for the mind to hold. The landscapes that fed sauropods were not uniform. A Jurassic floodplain could be wet for years and then dry enough for cracks to open in the mud. A river could shift course, abandoning one channel and cutting another. Lakes formed and disappeared. Forests advanced along water and thinned across drier ground. The giants moved through a world that changed under their feet. In the Morrison ecosystem, evidence of drought sits beside evidence of floods. Mudstones, sandstones, limestones, ripple marks, transported bones, and volcanic ash all speak to a landscape built by water and interruption. This was not a stable garden laid out for dinosaurs. It was a changing basin where life followed moisture
and sediment recorded the consequences. Conifers formed the tallest parts of many Jurassic plant communities. Some belonged to Araucarian lineages, relatives of trees that survive today mostly in the southern hemisphere. These trees could reach impressive heights, giving high-browsing sauropods access to food far above the reach of smaller herbivores. Their needles and branches were tougher than many flowering plant leaves, but they were abundant. Cycads occupied lower layers and open areas. They looked superficially like palms, but palms had not yet evolved. Their stiff fronds, thick trunks, and cone-like reproductive structures gave the Mesozoic understory a shape that is familiar in outline, but strange in detail. A sauropod feeding on cycads would be engaging with a plant world older in style than the forests around most people today. Ferns and horsetails grew in damp ground, along streams, pond margins, and disturbed areas. After floods or fires, ferns can recover quickly, and in the Mesozoic, they likely formed important low vegetation in many settings. Smaller herbivores fed there, but some sauropods with lower feeding envelopes may also have taken advantage of these dense, renewable patches. A sauropod moving along a river edge might pass through several feeding zones in a short distance. Tall conifers near the bank, cycad clusters on a slightly raised patch, fern thickets where sediment had recently been disturbed, horsetails in wet soil. The neck allowed choice without constant movement of the whole body. The absence of grass is worth remembering. A scene of giants crossing a green plain should not look like a modern savanna. Grasses existed only later and did not form the broad grassland ecosystems that would define much of the Cenozoic. Jurassic openness, where it occurred, was made of different plants and different textures. Flowers were absent through most of the Jurassic world and only became important later in the Cretaceous. That means no flower-rich meadows, no fruiting orchards, no bees in the modern ecological sense. Pollination, seed dispersal, plant chemistry, and insect communities all operated differently from the world outside the window now. By the Cretaceous, flowering plants began to spread, but they did not instantly replace older plant groups. Titanosaurs lived through this botanical transition. In some places, they browsed among conifers, ferns, and cycads, much as earlier sauropods had. In others, angiosperms became part of the available vegetation. The giant herbivore strategy adapted to changing plant communities. We cannot always say exactly what one species ate. Fossil teeth show form and wear. Coprolites, where confidently assigned, can preserve plant remains. Sediments show local vegetation, but direct meals are rare. The most accurate picture is usually a range of likely foods rather than a precise menu. Even so, the basic feeding challenge is clear. Sauropods had to take in large amounts of plant matter. Their success required productive landscapes. Warm climates, high carbon dioxide, long growing seasons in many regions, and extensive vegetation would all have helped support their biomass, though local drought and seasonal stress still mattered. The image of a giant eating can seem peaceful, but it is also an immense ecological force. Branches break, leaves vanish, paths form. Seedlings are trampled. Dung returns nutrients to the soil. Insects gather. Smaller animals follow disturbed ground.
A herd of sauropods could reshape a patch of forest simply by passing through it. Modern elephants give a partial analogy, but only partial. Elephants knock down trees, open paths, strip bark, disperse seeds, and alter habitats. Sauropods were not elephants, and their feeding mechanics differed. But as large herbivores, they likely had similar landscape-level effects in some environments. A sauropod footprint is therefore not only a trace of a foot, it can be part of a larger disturbance. Repeated paths may compact soil. Trampled vegetation changes recovery. Mud holes deepen. Small animals use the track as a pool after rain. A single step becomes a feature in the lives of other creatures. The giants also moved nutrients. Plant matter eaten in one place might be dropped as waste somewhere else. This is not a glamorous part of dinosaur life, but it matters. Huge herbivores are engines of nutrient transfer. Their bodies process vegetation and return it in forms that feed insects, microbes, plants, and soil systems. In that sense, the age of giants was also an age of quiet recycling. A conifer needle eaten by a sauropod became part of gut chemistry, then dung, then soil, then perhaps another plant. Deep time can be understood through bones, but it also passed through digestion, decay, and growth. Predators took part in that system as well. A carcass could feed theropods, crocodiliforms, insects, microbes, and scavenging vertebrates. Bite marks on sauropod bones show that large predators sometimes accessed these bodies. A dead giant would have been a temporary resource too large for one animal to monopolize completely. The death of a large sauropod near water could alter a site for weeks or months. The smell would carry. Tracks would converge. Bones would be exposed, dragged, chewed, and eventually separated. Floodwater might move them into a channel where sand buried them. Millions of years later, that disorder becomes a fossil assemblage. This is why bone beds can look chaotic. Paleontologists have to ask whether bones belong to one event or many, whether they died where they were found or were transported, whether a quarry represents drought, flood, predator trap, river concentration, or repeated accumulation over time. The answer matters because it changes the story. A group of sauropods preserved together might suggest social behavior, but it might also reflect a river that gathered bones from different places. A cluster of juveniles might indicate herd structure, or it might reflect preservation bias. Fossils speak, but they do not always speak plainly. The Morrison Formation has been studied for more than a century, yet it still invites new questions. New measurements, new stratigraphic work, new digital models, and new comparisons can change how old discoveries are understood. The famous formations are not exhausted simply because their names are familiar. A bone collected in 1909 can still become part of a 21st century study. It can be scanned, measured again, compared with newly discovered relatives, or placed in a revised evolutionary tree. The animal has been dead for over 100 million years, but the scientific life of its fossil continues. Tendaguru, Patagonia, the Neuquén Basin, the Gobi, the Isle of Wight, Portugal, Madagascar, India, and many other places each add a different angle to the sauropod story. Some preserve trackways, some preserve eggs, some preserve partial giants, some preserve smaller relatives that help explain the range of the group. The largest animals receive the most attention, but smaller sauropods are just as important scientifically. They show that the group was not defined only by maximum size. They occupied a range of body masses and habitats. Some lived on islands or in restricted environments where smaller size may have been favored. Others belonged to lineages that never approached the upper limits. Sauropods from late Jurassic Germany is a useful example. It was a small sauropod compared with its giant relatives, often interpreted as an island dwarf. Its fossils suggest that sauropod bodies could shrink under certain ecological conditions. The same basic plan that produced giants could also adapt to limited resources. That flexibility is easy to miss. When we say sauropod, the mind jumps to a giant neck above a museum hall. But evolution is not loyal to our icons. A lineage survives by changing.
Sometimes it grows. Sometimes it shrinks. Sometimes it spreads. Sometimes it disappears from one region and thrives in another.
Titanosaurs show this flexibility across the Cretaceous. Some were armored, some were enormous, some were relatively small. Some lived in semi-arid interiors, others near coasts or river systems. Their fossils appear on continents that had once been connected and were now increasingly separated, carrying dinosaur histories in different directions. The breakup of Pangaea and later Gondwana shaped sauropod evolution. As continents separated, populations were isolated. Sea levels rose and fell. Land bridges appeared and vanished. Climate belts shifted. The distribution of titanosaurs and other sauropods cannot be understood without the moving map beneath them. A dinosaur walking across a Cretaceous floodplain did not know that its continent was drifting. But over millions of years, continental motion changed rainfall, vegetation, migration routes, and isolation. Evolution works through bodies, but geology sets much of the stage. The Age of Giants is therefore also a story of continents. South America pulling away, Africa changing its coastlines, India moving northward, Antarctica carrying forests through high southern latitudes, North America divided at times by inland seas. The giants lived on ground that was never truly still. Climate shaped them too. The Mesozoic was generally warmer than the present world, though not uniformly warm and not stable in every interval. There were greenhouse conditions, regional droughts, humid belts, monsoonal patterns, coastal influences, and seasonal changes. Sauropods lived through variation, not a single permanent summer. It is tempting to link gigantism directly to warm climate or high plant productivity, and those factors likely mattered, but they are not enough by themselves. Warm worlds have existed without producing sauropods. The animals also needed the right anatomy, growth patterns, respiratory system, reproductive strategy, and evolutionary history. The largest dinosaurs emerged from a combination. Long necks expanded feeding envelopes. Small heads reduced neck weight. Air sacs lightened bones and improved breathing. Rapid growth reduced vulnerability. Egg-laying allowed many young. Large guts processed tough vegetation. Columnar limbs supported mass. Productive landscapes supplied food. Remove one part, and the system changes. A long neck with a heavy chewing skull would be harder to evolve. A large gut without enough vegetation would fail. Fast growth without enough eggs surviving would not sustain populations. Gigantism was not one invention. It was a chain of compatible traits. This is why mammals, despite their success after the dinosaurs, never matched sauropods on land. Mammals chew with heavy heads and complex teeth. They give live birth, limiting offspring size and number in different ways. Their breathing system lacks the same air sac-driven skeletal pneumaticity. They became large, but their root had other constraints. The comparison is not about superiority. Elephants are extraordinary animals. Paraceratherium, the giant hornless rhinoceros relative, was extraordinary in its own time. But sauropods followed another biological path, and that path reached farther into size than land mammals ever did. The land itself may also impose an upper ceiling. Bone and cartilage can only support so much. Muscles must move limbs. Feet must avoid sinking too deeply. Hearts must supply tissues. Heat must be managed. Food must be gathered. At the largest sizes, every system approaches a limit. That is what makes Argentinosaurus, Patagotitan, and their kin feel almost unreal. They stand near those limits. They show that life did not merely approach the edge of possibility on land. It walked there, fed there, reproduced there, and left bones large enough to unsettle anyone who sees them.
Apatosaurus deserves to be imagined with weight.
For a long time, it was tangled in public memory with the name Brontosaurus, a taxonomic confusion that became part of dinosaur culture. Scientific names changed, arguments continued, and recent work has again recognized Brontosaurus as distinct in some classifications. But whatever label is used for particular skeletons, the animal behind the debate was real, deep-bodied, powerful, and far from delicate. Apatosaurus had massive limb bones, a robust neck, and a heavy torso. It was not the longest sauropod of the Morrison, but it may have been among the most powerfully built. Its cervical vertebrae show a neck capable of carrying substantial muscle and ligament. Its body suggests an animal that moved with force rather than lightness. The skull of Apatosaurus was missing from early reconstructions, leading to mistaken heads being placed on mounted skeletons. That error lasted for decades in some displays and illustrations. It is a reminder that even famous dinosaurs can be assembled incorrectly when evidence is incomplete and assumptions filled the gaps too confidently. A wrong skull changes more than appearance. It changes feeding interpretation, posture, and public understanding. When paleontologists correct a mount, they are not just rearranging bones. They are bringing the animal closer to itself, or at least closer to what the evidence now supports. Diplodocus, by contrast, is often remembered for length. Its body stretched in a way that makes museum halls feel narrower. The neck extended forward, the tail extended backward. The skull was small and narrow, with teeth concentrated toward the front of the mouth. Its elegance can make it seem lighter than it was, but it was still a giant land animal. The tail of Diplodocus draws the eye almost as much as the neck. Vertebra after vertebra tapers toward a slender end. In life, it would have been carried above the ground or near it, depending on posture and movement, balancing the long front half of the body. The tail was not an afterthought. It was part of the animal's geometry. Diplodocids may have fed differently from Camarasaurus and other Morrison sauropods. Their skulls and teeth suggest selective cropping or stripping, perhaps at lower to middle heights, though different species may have varied. Their long necks allowed a broad feeding envelope. The body could stay relatively still while the head worked across vegetation. Camarasaurus was more compact and common in many Morrison deposits. Its skull was boxier and stronger, with broader teeth. It did not have the extreme length of Diplodocus, but it appears to have been successful across the landscape. Commonness in the fossil record may partly reflect preservation, but Camarasaurus clearly mattered in the Morrison ecosystem. A Camarasaurus feeding beside a Diplodocus would not simply be a smaller version of the same animal. Its head, teeth, neck proportions, and body shape imply a different relationship with plants. These differences are how ecosystems make room for several large herbivores. The animals divide the forest without drawing lines. Brachiosaurus is rarer in North America, but powerful in imagination. Its front limbs were longer than its hind limbs, giving it a high-shouldered profile. The related Giraffatitan from Tanzania is known from more complete material and has often carried the public image of a towering sauropod reaching into tall trees. The classic high-browsing sauropod is not a myth, but it should not be applied to every long-necked dinosaur. Brachiosaurids were well suited to reaching high vegetation. Diplodocids may not have lived the same way. Mamenchosaurids stretched neck length in a different pattern. Titanosaurs varied. The neck alone does not determine the feeding style. Neck posture has been debated for decades. Early art often raised sauropod necks like vertical periscopes. Later work sometimes lowered them dramatically. Current views tend to be more nuanced, recognizing that different species had different anatomy and that living tissue, cartilage, and muscle affect range of motion in ways bare bones do not fully capture. Mamenchosaurus and its relatives invite the most direct attention to the neck. Some had astonishingly elongated cervical vertebrae, producing proportions that seem almost excessive until viewed through the lens of feeding efficiency. A long neck allows access, and access becomes survival when plant resources are patchy, vertical, or divided among many herbivores. A mamenchosaurid neck moving through a Jurassic forest would have been one of the strangest shapes in terrestrial history. Not a snake, not a crane exactly. A living bridge between a heavy body and a small head, held by vertebrae full of air and muscle, arranged to keep the impossible usable. Sauropods, from the early Cretaceous of North America, carries another image of height. Its enormous cervical vertebrae suggest a tall brachiosaurid or brachiosaur-like animal that may have reached vegetation at remarkable levels. It lived after the classic Jurassic giants, showing that the high-browsing body plan continued into the Cretaceous. Not every famous giant belongs to the same lineage. Diplodocus was a diplodocid. Brachiosaurus was a brachiosaurid. Argentinosaurus and Patagotitan were titanosaurs. Sauropods was related to brachiosaurids. These distinctions matter because they show multiple routes to great size, not one straight ladder. Fossils from Portugal, Spain, England, China, Tanzania, Argentina, and the United States have all contributed to this branching story. Some discoveries are famous because they are large. Others are famous because they preserve rare anatomy. Some are important because of where they were found, filling a gap in geography or time. A small vertebra can be as meaningful as a huge femur if it belongs to the right part of the tree. A tiny tooth can reveal a sauropod presence in a formation where no skeleton has been found. A trackway can show that a giant walked through a region even if its bones never survived there. The fossil record is a mosaic, and sauropods appear in different pieces. Sometimes the body is there, but not the head. Sometimes the feet are there only as impressions. Sometimes eggs are present without adults. Sometimes a single bone gives a name, and future discoveries decide whether that name remains useful. Dinosaur names are not permanent monuments. They are scientific hypotheses attached to fossils. Some endure, some are revised, some are merged with others, some return after being dismissed. Public culture often wants a stable list, but paleontology is a living discipline, and the giants are still being sorted. Brontosaurus is the familiar example. Once treated as a synonym of Apatosaurus for much of the 20th century, it has been revived by some studies as a valid genus based on detailed anatomical differences. The debate illustrates how old fossils can become new again when examined with broader datasets and more precise methods. This does not mean every old name should return, or every new claim is final. It means classification depends on evidence, comparison, and interpretation. Sauropod taxonomy is difficult because many species are known from incomplete skeletons, and giant bodies can vary with age, growth, and individual differences. Age matters. A juvenile may look proportionally different from an adult. A subadult giant may not have reached its final body mass. Bone surfaces, growth tissue, and fusion of skeletal elements can help estimate maturity, but not always with perfect certainty. A huge individual might still have been growing. That possibility is unsettling. Some of the largest animals known from fossil bone may not have reached full size. Dreadnoughtus, for example, has been described as not fully grown at death. The animal preserved in stone was already immense, and yet its life, if uninterrupted, might have carried it farther. Growth did not continue forever, but the upper curve is hard to trace when complete life series are rare. Ideally, scientists would have hatchlings, juveniles, subadults, and adults from the same species. For most sauropods, the record is far less generous. Growth histories have to be built from scattered individuals, bone tissues,
and comparisons.
Bone histology helps because it preserves growth signals inside the skeleton. Thin sections can reveal vascular patterns, lines of arrested growth, remodeling, and maturity indicators. Studying a giant dinosaur sometimes requires cutting a small piece from a bone, a destructive act done carefully because the information inside can be worth the loss.
The result is a more dynamic animal. A sauropod is not just an adult outline, it is a growth curve. It begins in an egg. It grows through dangerous years. It changes proportions. Its bones remodel under stress. Its feeding height shifts. Its role in the ecosystem changes as its body expands. The museum skeleton freezes one moment, usually adulthood or near adulthood. The living animal was never frozen. It was always becoming something else until growth slowed and age began its own quieter work. Old sauropods must have existed, though they are hard to recognize. Worn teeth were replaced, but joints, bone surfaces, healed injuries, and disease can leave traces. A giant that survived predators and drought still faced the slow injuries of weight, movement, and time. The largest bodies carried the largest histories of stress. Some sauropod bones show pathologies, healed fractures, infections, abnormal growths, and other changes.
These are not distractions from the grand story. They are intimate evidence. They show an animal that lived long enough to be hurt and continue, long enough for bone to respond. A healed injury in a giant limb suggests survival under conditions that would challenge any animal. How did it move while injured? Did others travel nearby? Did it fall behind? Did it feed differently? The fossil cannot answer all of that, but it turns a category into an individual for a moment. The age of giants was made of individuals, not just species, not just clades. One animal hatched in a particular season, avoided a particular predator, crossed a particular river, broke or did not break a bone, reached or failed to reach full size. Deep time can make life seem anonymous, but every fossil body belonged to one animal before it belonged to science. That is easy to forget when discussing tons and meters. Measurements flatten the living animal into data, and data is necessary. But behind the measurements were hunger, movement, fear, rest, heat, irritation, growth, and the constant work of staying alive. A sauropod did not know it was pushing a biological limit. It knew, in whatever way its nervous system knew, where food was, where footing was safe, where other bodies moved, where water lay, and when something in the environment required attention. The record-breaking scale was a human discovery made long after the animal stopped needing anything. The same is true of Titanosaurs. Patagotitan did not live as a title holder. Argentinosaurus did not move through Patagonia as a symbol of maximum land life. These animals were not made for us. They were made by their worlds, and the worlds disappeared. Consider the head again. It is small only in proportion to the body. On its own, it is still the head of a large animal, with eyes, nostrils, jaws, teeth, and muscles, arranged around the needs of feeding and awareness. The face of a sauropod was not built for expression in a mammalian way, but it was not blank. The eyes faced outward enough to watch a broad field. The nostrils opened on the skull in positions that have been reconstructed differently over time. The mouth carried teeth suited to cropping rather than grinding. The brain was small relative to the body, but that does not make the animal stupid in any useful sense. It had the nervous system it needed for its way of life. Intelligence should not be measured by how much an animal resembles a human. A sauropod needed spatial awareness, feeding choices, social recognition if it lived in groups, responses to predators, memory of water or roots, and control of an enormous body. Its cognition was shaped by being a sauropod, not by failing to be something else. Movement at that scale was probably deliberate. This does not mean slow in every context, but acceleration becomes costly as size increases.
A giant animal does not turn like a small predator.
It plans its body through space. It places feet where weight can be held. It avoids ground that might trap it. Bad ground could be deadly. A river margin that looks firm may give way under a mass that no smaller animal would notice. Mud can hold a foot, and a stuck foot can become a crisis when the body above it weighs many tons. The fossil record of trackways sometimes captures slipping, sinking, or uneven surfaces, small moments where the ground answered back. Sauropods likely followed familiar routes when conditions allowed. Repeated movement through landscapes can create trails. Modern large herbivores use paths to water, feeding grounds, and safe crossings. Sauropods may have done the same, especially where herds or repeated seasonal movements concentrated traffic. Imagine a trail worn between conifers and a river bend. The soil is compacted by old steps. Ferns grow lower along the edges where bodies have brushed past. Smaller animals use the cleared path because the giants made it easier. A sauropod trail could become part of the ecosystem, a road built without intention. Sound is harder. Sauropod vocal organs did not fossilize, and birds and crocodilians offer different clues from opposite sides of the dinosaur family tree. They may have produced low-frequency calls, visual displays, body movements, or other signals. The long neck and large body invite speculation, but certainty is limited.
It is safer to say they communicated somehow.
Large animals with social lives, mating behaviors, alarm responses, and group movement need signals. Whether those signals were deep calls, hisses, bellows, postures, tail movements, or combinations is difficult to know. The silence of fossils is not evidence that the animals were silent. Low-frequency sound would make sense for large animals, because deep sounds travel far and are common among some large modern animals. But the exact production mechanism in sauropods remains uncertain. Any reconstruction of their voices belongs partly to science and partly to imagination. A herd calling across a floodplain is a beautiful image. It may even be plausible. But the rock does not preserve the sound. It preserves the footfall, the bone, the eggshell, the tooth, the sediment around them. The voice is one of the things deep time kept for itself. Predators left clearer traces. Teeth preserve well. Bite marks sometimes remain. Theropod skeletons show weapons shaped by flesh-eating. In the Jurassic, Allosaurus was one of the major predators of the Morrison world. In the Cretaceous southern continents, Carcharodontosaurids, Abelisaurids, and other theropods shared landscapes with Titanosaurs at different times and places. A predator facing sauropods had choices. It could scavenge carcasses, target young animals, follow herds for vulnerable individuals, attack the sick, or ignore the biggest adults, except in rare circumstances. The existence of huge prey did not mean constant attacks on huge adults. Predation is about risk as much as hunger. A juvenile titanosaur separated from cover was one kind of opportunity. A dead adult was another. A weakened subadult near a drying waterhole was another. The dramatic image of a theropod leaping at a healthy giant may make good art, but the ordinary strategies of survival were likely more cautious.
Still, violence happened. A tooth entering flesh, a tail swinging, a herd shifting away from a scent, a young animal vanishing at the edge of vegetation. The Mesozoic was not gentle. It was also not a continuous battlefield. Most days in any ecosystem are made of avoidance, feeding, watching, and waiting. Large size changes predator behavior. A predator that cannot kill an adult may still follow a group for days, watching for a calf, waiting for injury, feeding on dung-associated animals, or searching the same water sources. The giants influenced predators even when they were not attacked. Scavenging is sometimes treated as less impressive than hunting, but in real ecosystems, it is vital. A sauropod carcass was a massive concentration of energy. Theropods, crocodiliforms, insects, and microbes would have used it. Even bones, once stripped, became mineral structures in a landscape of decay and renewal.
Bite marks can show where jaws met bone after flesh was removed, or during feeding near the skeleton. Some marks on Morrison bones show theropod contact. They do not always tell us whether the predator caused the death. A carcass can become evidence for many interactions after the animal is already gone. Look at a sauropod rib with tooth grooves along its surface, and the scene becomes almost close. A predator pulling at flesh, the bone exposed, serrations scraping. Perhaps the body lies in a river channel. Perhaps flies or beetles gather. Perhaps floodwater will arrive in a day and scatter the remains. The fossil does not care which version is more exciting. It only preserves the groove. The scientist measures it, compares it to teeth, studies its depth and shape, and asks what kind of contact could have made it. The drama is secondary to the mark. Sauropod defensive behavior is mostly inferred. They had tails, size, group movement, and possibly vigilance. Some titanosaurs had osteoderms. Adults were hard targets. But we should be careful about turning every tail into a weapon and every herd into a defensive wall. Animals use bodies in many ways, and not all uses fossilize. A tail strike from a large sauropod could injure a predator if it connected, but how often that happened is unknown. More often, size alone may have reduced the need for active defense. Predators tend to avoid injuries that could prevent future hunting. A risky meal is not always worth taking. The most important defense was probably growing large. Once an animal passed a certain size, the predator community changed around it. It did not become immortal. It became expensive to attack. That difference may have shaped sauropod life history as much as any dramatic weapon. The pressure on young animals would have remained severe. Fossil nesting grounds show the beginning of life, but not the countless losses afterward. Eggs can be eaten, hatchlings can be taken, juveniles can fail in drought. The adult giant is the survivor's form, not the average fate of every egg. This gives the skeleton of an adult a quiet meaning. It is not only big, it is successful. It passed through a world that removed many others before they could leave more than shell fragments or tiny bones. Some sauropods may have lived in age-segregated groups. Evidence from trackways and bone beds has been interpreted in different ways, but the idea is plausible. Young animals with different feeding needs and vulnerability might travel together. Adults might move separately or gather under particular conditions. Mixed groups may also have occurred. We cannot impose modern elephant society directly onto sauropods. Elephants are mammals with live birth, long parental care, complex matriarchal groups, and very different brains. Sauropods were dinosaurs laying eggs, growing rapidly, and living under different ecological rules. Analogies can help, but they can also mislead. Birds and crocodilians give other clues, but they too are imperfect. Birds are living dinosaurs, yet most are small, feathered, and very unlike sauropods in body plan. Crocodilians are distant archosaur relatives with their own ecology. Sauropod behavior must be reconstructed from a triangle of fossils, living relatives, and physical possibility. What seems reasonable is that sauropods were not solitary machines. Trackways, nesting sites, and bone accumulations suggest that groups formed at least sometimes. Whether those groups were stable herds, temporary gatherings, age classes, migration bands, or nesting congregations may have varied by species and circumstance. Migration is another difficult question. Large herbivores often move to track food and water. Some sauropods may have ranged widely across floodplains and basins. Others may have remained within regions where resources were reliable. Isotopes in teeth and bones can sometimes hint at movement, but the picture is still incomplete. A moving herd would not need a dramatic destination. It might follow a drying river toward remaining pools, leave a browsed area for a regrowing one, or cross higher ground after floodwaters retreated. The reason could be simple. Food here is gone, water there remains. The body moves because life requires it. Seasonality shaped these decisions. Even greenhouse climates had wet and dry periods in many regions. The Morrison Formation records drought episodes. Cretaceous floodplains could be seasonal. Plant growth, nesting, water availability, and predator concentration all shifted through the year. Drought may have been one of the great enemies of giants. A small animal can sometimes hide, burrow, or survive on little. A giant needs volume. It needs water and plant matter at a scale that becomes dangerous when landscapes dry. A drought does not have teeth, but it can kill more effectively than any predator. Dry seasons could concentrate animals around shrinking water sources. That concentration increases competition, disease, predation, and the chance of mass death. Some fossil bone beds may reflect such moments, though each site requires its own evidence. The age of giants was also an age of environmental stress. Floods could be just as important, but in a different way. A flood might kill, transport, and bury. It might preserve what drought began. A weakened animal dies near a channel. Later, water moves the bones. Or a flood catches animals suddenly. Either way, the sediment becomes the archive. In Patagonia, repeated flood events are part of the story of Patagotitan. In the Morrison, river channels preserved many bones. Across the world, the same basic principle appears. Water destroys bodies and saves them, tears skeletons apart, and covers them before the last evidence is lost. The giants needed water in life. They often needed water again in death, not for survival, but for preservation. Volcanic ash also helped. Ash layers can bury landscapes, alter soils, and provide minerals. More importantly for scientists, crystals in ash can sometimes be dated radiometrically, tying fossil layers to numerical ages. A dinosaur bone in sediment near ash is not just an object. It becomes part of a timeline. Dating is essential because sauropod evolution spans such long intervals. The difference between an early Jurassic sauropod and a late Cretaceous titanosaur is not a small gap. It can be more than 100 million years. That is longer than the time between Tyrannosaurus and the present. Deep time can flatten in public imagination. Jurassic and Cretaceous dinosaurs are often placed together as if all giants shared one world. But Diplodocus never saw Argentinosaurus. Brachiosaurus never crossed paths with Patagotitan. These animals were separated by changing continents, changing plants, changing predator faunas, and tens of millions of years. The age of giants was long enough for giants to become history to other giants. A Cretaceous titanosaur lived in a world where the classic Jurassic sauropods were already ancient dead, though no animal there knew it. Deep time contains its own deep time. This is why the title cannot mean a single scene. It means a long succession. Early experiments, Jurassic expansion, late Jurassic diversity, Cretaceous transformation, Titanosaur dominance,
final survival until the end of the dinosaur age. The giants were not a moment.
They were an era within an era. Scientific understanding of sauropods depends on methods that would have been impossible for the first fossil hunters. CT scanning can reveal internal spaces without cutting into a specimen. Photogrammetry can turn bones and trackways into digital models. Histology can show growth. Geochemical work can hint at diet, climate, or movement. Old bones keep offering new information because the questions keep changing. A vertebra that once proved only that a large animal existed may now reveal pneumatic structure, stress distribution, and evolutionary relationships. A trackway, once described with sketches, can now be mapped in 3 dimensions, preserving the depth and deformation of each print. A quarry, once interpreted as a single event, can be re-examined layer by layer. The tools are modern, but the work still begins with observation. A paleontologist kneels beside stone and notices texture, color, shape, and contact. Bone differs from rock in subtle ways. The curve of a shaft, the honeycomb of internal structure, the smoothness of a joint surface. Science begins before the instrument, in the trained eye. In the field, sauropod bones often appear as puzzles too large to see at once. A vertebra may be exposed on one side while the rest disappears into a hill. A femur may lie partly beneath other bones. A rib may curve through sediment from meters. The skeleton can be present but unreadable until the surrounding rock is removed. Excavation is slow because the fossil is both precious and damaged. It may be cracked by weather, crushed by geological pressure, invaded by roots, split by erosion, or weakened by its own size. The goal is not simply to pull it out. The goal is to preserve as much information as possible, including its position in the rock. A bone without context loses part of its meaning. The layer, orientation, nearby fossils, sediment type, and relationship to other bones all matter. Was the skeleton articulated? Were the bones aligned by current? Were there teeth nearby? Was the animal buried where it died? These questions are answered by context as much as by anatomy. This is why modern paleontology records quarries carefully. Maps, photographs, coordinates, stratigraphic notes, plaster jackets, field numbers, and lab records become part of the scientific specimen. The fossil is not only the bone. It is also the information that proves where and how the bone was found. In early dinosaur history, some of that information was lost. The rush to collect spectacular skeletons sometimes outpaced careful documentation. Rivalries, museum competition, and the sheer novelty of giant bones shaped the first public images of sauropods. The animals were famous before they were fully understood. The bone wars of the 19th century gave the world many dinosaur names, including some sauropods, but it also produced confusion. Marsh and Cope competed fiercely, naming animals from incomplete material and sometimes making mistakes. Their work was foundational and flawed, like much early science carried out under pressure. From that period came the public love of long-necked dinosaurs. Mounted skeletons became cathedral-like displays of deep time. A sauropod in a museum is not just an exhibit. It changes the scale of the room. People instinctively look up. They measure themselves against the leg, the rib cage, the neck. Few fossils alter human postures so quickly. Stand beside the cast of a giant femur, and the body reacts before the mind finishes calculating. The animal becomes physical, not distant. Deep time is suddenly taller than you. Museum mounts, however, are interpretations. Missing bones may be mirrored from the opposite side or reconstructed from relatives. Posture reflects scientific opinion at the time of mounting.
Tail height, neck angle, limb spacing, and skull shape may change as understanding improves. A mounted sauropod is a scientific argument made visible. This does not make the mount false. It makes it provisional. Museums balance evidence, engineering, public display, and current interpretation. The most honest displays often show which bones are real, which are casts, and which are reconstructed.
Transparency matters because the animal is too important to be presented as more certain than it is. The same caution applies to size charts. A row of dinosaur silhouettes can be helpful, but it can also hide uncertainty. A neat outline of Argentinosaurus may look precise even when the skeleton behind it is fragmentary. A length estimate may depend on relatives. A mass estimate may depend on a model invisible to the viewer. Length and mass are different kinds of size. Diplodocus was very long, but not as heavy as the greatest titanosaurs. Brachiosaurids could stand tall at the shoulder and reach high, while some titanosaurs were broader and heavier. The longest animal is not always the heaviest. The tallest is not always the most massive. This matters when discussing the biggest animals on land. A single ranking can mislead. Patagotitan is better represented than some rivals, but its exact mass is debated. Argentinosaurus may have been heavier, but it is known from fewer pieces. Dreadnoughtus is unusually complete for a giant titanosaur, yet its mass estimate has been revised downward by some researchers. The fairest answer is that several titanosaurs occupy the upper range. Argentinosaurus, Patagotitan, Puertosaurus, Dreadnoughtus, Notocolossus, and others are part of the conversation, with confidence varying by specimen. The question is not only which animal was biggest, it is how close several lineages came to the maximum possible size. Another complication is density. A sauropod body was not a simple block of meat. Air sacs, lungs, pneumatic bones, gut contents, fat, muscle, and soft tissue all affected mass. Two reconstructions of the same skeleton can produce different body volumes, and different assumptions about density can change the weight. This is why a number like 70 tons should feel impressive but not final. It is a scientific estimate, not a scale reading from a living animal. No one weighed Patagotitan. No one measured Argentinosaurus nose to tail while it stood still. The numbers are careful shadows cast by bones. The shadows are still powerful. Even conservative estimates place the largest sauropods far beyond modern land animals. An African elephant is immense in the living world, yet several titanosaurs may have weighed many times as much. The comparison helps, but only up to a point. At sauropod scale, familiar references begin to fail. 10 elephants, 12 elephants, a building, a bus, a basketball court. These comparisons are useful because the human mind needs handles. But the animal was not made of elephants or buildings. It was one body, continuous and alive, with blood moving through it and food passing through it, and muscles pulling bone against bone. The living animal would have been stranger than its measurements. Skin stretched over the ribs, the flank expanded with breath. The neck shifted to feed. The tail adjusted balance. The foot sank. The eye moved. A bird-like respiratory system, a reptile-like egg, a dinosaur body, and a scale no living land animal can show us. That is the difficulty of sauropods. They are familiar enough to be beloved and strange enough to resist complete imagination. Public images have changed from swamp-bound brutes to active land animals, from tail-dragging silhouettes to tails held clear of the ground, from sluggish, cold-blooded monsters to animals with complex growth and physiology. Each revision removes one old assumption and replaces it with something better supported, often more interesting. Trackways played a major role in correcting tail dragging reconstructions. Many sauropod trackways show footprints without tail marks between them. This suggests that the tail was usually carried off the ground, not dragged like a heavy rope. A missing line in the mud changed how artists drew the animals. This is one of the elegant parts of paleontology. Absence can matter when preservation conditions are right. If soft mud recorded feet clearly but no tail drag appears, the animal's posture is constrained. The trackway becomes a witness not only to where feet went, but to where the tail did not. Posture affects emotion in art. A tail dragging on the ground makes an animal look sluggish and burdened. A tail held aloft makes it look balanced and alive. The scientific correction changed the mood of the dinosaur, not by adding drama, but by bringing it closer to how it likely moved. Neck posture has been revised more cautiously because evidence is complicated. Vertebral joints, cartilage, muscles, ligaments, and behavior all interact. Some sauropods may have raised the neck high often. Others may have held it closer to horizontal. The range of motion in a living neck cannot be read from dry bones alone. Modern animals warn us about this. Skeletons can understate or overstate flexibility, depending on missing cartilage and soft tissues. Ostriches, mammals, and reptiles all show that joints in life do not behave exactly like cleaned bones on a table. Sauropods were no different, except much larger and extinct. The most useful approach is species by species. Brachiosaurids, Diplodocids, Mamenchisaurids, and Titanosaurs should not all be forced into one posture. Their vertebrae, limb proportions, shoulders, and feeding anatomy differed. The giant body plan allowed variation, and variation is where much of the story lives. Variation also appears in tooth replacement. Some sauropods replaced teeth rapidly, keeping fresh cropping surfaces available despite wear from tough or abrasive plants. Diplodocids and some titanosaurs show high replacement rates compared with animals that relied on more durable chewing teeth. The mouth was a conveyor of tools. A tooth could form, erupt, wear, and be replaced while the animal continued feeding. Isolated sauropod teeth in sediment sometimes represent this constant turnover. They are small compared with the skeleton, but they reveal the rhythm of daily life more directly than a giant femur does. A shed tooth in mud is a quiet fossil. It does not announce a huge body the way a limb bone does. But it may be the trace of one feeding moment. The head lowered, the jaws closed on vegetation. A worn tooth loosened and fell. The animal moved on, leaving a tiny piece of itself behind. Such fossils are reminders that the age of giants is also an age of small evidence. Eggshell, teeth, skin impressions, gastrolith candidates, coprolites, pollen, spores, insect traces, and plant fragments all help build the world around the bones. Without them, the giants float in empty space. A good reconstruction needs the world. The sauropod body makes sense only with the plants it ate, the ground it crossed, the climate it endured, the predators it avoided, the eggs it laid, and the sediment that preserved it. Size is the beginning of the question, not the end. The Cretaceous titanosaur world was different from the Jurassic sauropod world in ways that go beyond names. Continents were farther apart. Flowering plants were increasingly present. Predator faunas had changed. In South America, large Carcharodontosaurids dominated some earlier Cretaceous ecosystems, while Abelisaurids became important later. Crocodiliforms, turtles, fishes, pterosaurs, birds, mammals, and insects filled the spaces around the giants. In the Huincul Formation, where Argentinosaurus is from, the ecosystem included other enormous dinosaurs, including giant predators and large herbivores. The landscape was not a simple stage with one titanosaur on it. It was a community of huge bodies, smaller bodies, water channels, vegetation, heat, dust, and seasonal change. The presence of predators such as Mapusaurus in roughly similar regional and temporal contexts has encouraged speculation about interactions with giant sauropods. But as with Allosaurus and the Morrison giants, the safest interpretation is cautious. Large theropods may have scavenged titanosaurs, targeted vulnerable individuals, or hunted in ways that rarely involved healthy adults at full size. A predator beside a titanosaur carcass does not need to have killed it. Death creates opportunities. Drought, disease, injury, flood, old age, or accident may provide what teeth later mark. The fossil record often preserves feeding more readily than hunting. Carcharodontosaurids were formidable animals with blade-like teeth suited for slicing flesh. Abelisaurids had shorter skulls, powerful necks, and reduced forelimbs. These predators belonged to different lineages and strategies. Titanosaurs lived under pressure from a changing theropod world, not one repeated predator type. A late Cretaceous floodplain in South America might hold a narrow-headed titanosaur feeding among shrubs and conifers, small mammals moving under cover, birds calling from branches, crocodiliforms near channels, and an abelisaurid moving along the edge of vegetation. The scene belongs to the end of the dinosaur age, but it is not dying yet. That point matters. The final Cretaceous was not a world of dinosaurs already fading into weakness everywhere. Titanosaurs were still diverse and widespread. In many southern regions, they were among the major herbivores. The age of giants continued almost to the last day when the asteroid impact changed everything. 66 million years ago, a body from space struck Earth near what is now the Yucatan Peninsula. The impact triggered fire, darkness, cooling, acid rain, disrupted food webs, and global environmental collapse. Non-avian dinosaurs disappeared, including every sauropod and titanosaur. The largest animals on land did not survive the boundary. Their size, so useful in stable ecosystems, may have become a liability under sudden collapse. Large herbivores need large amounts of food. If photosynthesis is interrupted and plant communities crash, a giant body becomes hard to maintain. Eggs, young, adults, and entire populations would face conditions outside the range their lineage had endured. Extinction at the end of the Cretaceous was not caused by one simple pressure acting equally everywhere. The impact created a cascade. Darkness reduced plant growth, food webs failed, temperatures shifted, fires and atmospheric chemistry added stress. The survivors were often small, adaptable, aquatic, burrowing, seed-eating, or otherwise able to pass through scarcity. Birds survived, meaning dinosaurs survived in one branch, but sauropods did not. Their lineage, after more than 100 million years of success, ended. No long-necked giant crossed into the Cenozoic. The world of mammals would grow large animals later, but the sauropod experiment was over. A titanosaur nest on the last Cretaceous floodplain would not have looked like an ending. Eggs in sediment, adults moving nearby or elsewhere, plants growing, insects entering small cracks. The day before catastrophe, life was simply continuing. That is one of the hardest things about extinction. It becomes obvious only afterward. The final animals do not know they are final. The last sauropod to lift its head among Cretaceous plants did not carry the knowledge that no animal like it would ever walk again. After the boundary, the bones remained. Some were buried already, others weathered from fresh dead bodies and vanished. Over time, sediments hardened, continents moved, mountain ranges rose, rivers cut down through layers.
The giants passed from life into geology. The mammals that inherited the Cenozoic did not immediately fill the world with elephants and rhinos. Large body size took time to evolve again. Even then, no land mammal reached the upper scale of the greatest sauropods. The absence they left was never completely refilled. This is not because mammals failed. Mammals followed their own rules. They developed complex teeth, lactation, live birth, fur, high metabolic rates, and different life histories. They became whales in the water, bats in the air, primates in trees, horses on plains, elephants in forests and savannas. But the sauropod route to land gigantism did not reopen. In the modern world, the closest living dinosaurs are birds. A sparrow on a fence is more closely connected to the dinosaur age than any crocodile or lizard. But birds are theropods, not sauropods. The long-necked giants have no living descendant that preserves their body plan. This creates a strange imbalance. Dinosaurs survive all around us, singing in trees and crossing sidewalks. Yet one of the most iconic dinosaur forms is entirely gone. The living dinosaur world carries feathers and beaks, not columnar limbs and 40-foot necks. Sauropods remain through traces, trackways on exposed rock, eggs in nesting horizons, vertebrae in museum drawers, mounted skeletons in halls, teeth in collections, quarry maps, plaster jackets, scientific papers, children's drawings.
The age of giants continues, as evidence and imagination working together.
A child standing under a sauropod mound may not know the difference between a diplodocid and a titanosaur. They may not know about pneumatic vertebrae, tooth replacement, or body mass debates. But they understand scale immediately. The first lesson is not technical, it is physical. The world was once able to hold this. From there, the details can follow. The neck was lightened by air spaces. The head was small. The teeth were replaced. The gut was large. The eggs were small compared with the adult. The tracks show movement. The bones show growth. The sediment shows place. The debate shows science still working. This is how wonder becomes knowledge, without losing wonder. A giant bone draws attention. Careful study turns attention into understanding. The animal becomes more complex, not less, as the mystery is examined. There is a temptation to treat sauropods as impossible creatures that somehow slipped past the rules. But they did not break biology. They used biology fully. Their bodies followed physical constraints, exploited inherited traits, and evolved solutions that worked under Mesozoic conditions. The result feels impossible because nothing like it exists now.
The better word may be improbable. Sauropods required a rare alignment of traits and environments. Once that alignment existed, evolution explored it repeatedly. Long necks became longer, bodies became heavier, air-filled bones became more elaborate, feeding systems became more efficient. Some lineages shrank, but others climbed toward the ceiling. The ceiling itself remains uncertain. How heavy could a land animal become before bone, cartilage, blood pressure, heat, or food supply failed? The largest titanosaurs may lie near that limit, but not necessarily exactly at it. The fossil record may not have preserved the true maximum. Or it may have, and we have not recognized it yet. Claims of even larger sauropods sometimes appear from fragmentary material. A partial vertebra, a broken limb, an old measurement, a lost specimen. Some may represent truly enormous animals. Others may be misestimated, misassigned, or too incomplete for confidence. Scientific caution is not an attempt to make the giants smaller. It is an attempt to keep them real. Brachiosaurus, once tied to the famous and controversial Amphicelius material, shows how difficult this can be. Historical descriptions suggested an enormous vertebra, but the original fossil was lost. Without the specimen, later researchers must work from drawings and notes, making extreme size claims uncertain. The lost bone becomes almost a ghost in the literature. A missing fossil can haunt science. It once existed, perhaps. Someone saw it, measured it, drew it, named it. Then it vanished. What remains is not bone, but a question about bone. Other giants are more secure because the material can still be studied. Patagotitan's bones exist. Dreadnoughtus exists. Argentinosaurus, though fragmentary, exists in preserved elements that can be measured and compared. The strength of a claim depends not only on size, but on the survival of the evidence behind it.
This is why completeness matters.
A slightly smaller animal known from many bones may teach more than a larger animal known from one fragment. The most informative fossil is not always the record holder. Paleontology values context, anatomy, and comparison as much as superlatives. Even the smaller sauropods contribute to the question of giant size. Sauropods helps show how size can decrease. Early sauropodomorphs show the pathway before full gigantism. Medium-sized titanosaurs show diversity within the final radiation. The extremes make sense only when placed among the ordinary members of the group. The ordinary members were not ordinary in life. A 10-ton sauropod would still dominate any modern landscape. It seems modest only because its relatives grew absurdly large. Scale inside the sauropod family can distort our sense of size. A Camarasaurus that seems compact beside Diplodocus would tower over most living land animals. A Saltosaurus that seems small beside Argentinosaurus would still be a major herbivore. The family of giants contains its own internal giants and dwarfs, but the baseline is already far beyond the familiar. This is the age of giants in the fullest sense. Not only the greatest species, but entire ecosystems where multi-ton herbivores were common, where long necks moved through forests across continents, where footprints the size of basins could be part of an ordinary morning. The story also changes how we see the Mesozoic plant world. Forests without flowers fed animals larger than any land mammal. Conifers, cycads, ferns, ginkgos, and horsetails supported food webs rich enough for sauropods, stegosaurs, ornithopods, theropods, pterosaurs, mammals, insects, turtles, and more. Modern plants are not required for complexity. The Jurassic and Cretaceous worlds were not unfinished versions of ours. They were complete ecosystems on their own terms. Their plants reproduced, their animals fed and nested, their rivers shifted, their climates changed, their communities succeeded for millions of years. They did not wait for grass, flowers, or humans to become real. Sauropods belonged to those worlds so completely that removing them from context makes them harder to understand. A giant skeleton in a white museum hall is magnificent, but it is incomplete until the floodplain returns around it. The mud, the trees, the heat, the insects, the predator at a distance, the eggs under sediment, the sound we cannot hear. Return to the quarry where the script began. The bone in the hillside is still partly stone, partly animal. Around it are grains of sediment laid down by water, perhaps with ash from volcanoes, perhaps with plant fragments too small to notice at first. The giant is not alone, even in death. Its world is buried with it. A paleontologist marks the position. Tools remove the overburden. The exposed surface is stabilized. Plaster wraps the fossil. A machine may lift what human arms cannot. The bone leaves the ground slowly, not as treasure taken from a tomb, but as evidence entering a longer conversation.
When the jacket closes, the fossil disappears for a while.
White plaster replaces visible bone. Labels record what the eye can no longer see. The giant is carried away in silence, still heavy, still incomplete, still waiting. Later, in a laboratory, the plaster opens. Rock falls away under careful tools. The bone returns, cleaner now, but not less ancient. Measurements begin. Comparisons begin. The animal receives or confirms a name. A drawing appears in a paper. A life reconstruction follows. The public sees the giant rise again in outline. None of this brings the animal back. It brings back understanding. The difference matters. A fossil is not resurrection. It is contact across time, limited and powerful, with something that cannot answer except through the form it left behind. The form left behind is enough to change the room. A sauropod vertebra on a table has weight even before anyone explains it. The processes rise like buttresses. The hollows open into darkness. Broken edges reveal internal architecture. It looks engineered, but it was grown, cell by cell, inside a body that needed to eat. The same is true of a femur. Its surface may be scarred by preparation, cracked by time, repaired with consolidant, but the shape still carries the force it once resisted. At the ends, the joint surfaces held cartilage. Along the shaft, muscles pulled. Inside, blood vessels once nourished living bone. The fossil is mineral now, but its geometry remembers strain. Body mass estimates begin with such geometry. Scientists measure limb circumferences, reconstruct volumes, compare with living animals, calculate scaling relationships, and test models against what physics allows. Each method has strengths and weaknesses. Limb scaling uses the relationship between support structures and weight. Volumetric models estimate the space the animal occupied. Both require assumptions. For smaller animals, those assumptions may produce tolerable margins. For giant sauropods, small differences become large. A slightly thicker torso, a lower density, a different neck posture, or a broader rib cage can change estimates by several tons. The numbers are not guesses, but they are not exact either. This is why the largest sauropods are best discussed with ranges. Patagotitan may be described within a range that extends from the low 40s to above 70 tons, depending on method. Dreadnoughtus has been estimated very high and then argued lower. Argentinosaurus remains among the heaviest candidates, but fragmentary evidence keeps the range open. What all serious estimates agree on is that these animals were beyond anything alive on land today. That agreement is more important than the exact ranking. Whether one giant weighed 55 tons or 75, it belonged to a biological category that has vanished from Earth. A living African elephant is already enough to make the ground feel occupied. A full-grown giant titanosaur may have weighed many times more. It would not need to move quickly to dominate attention. Its breathing, its shifting stance, its shadow, and the slow displacement of vegetation around it would be enough. Yet the animal also had limits. It could not leap. It could not turn instantly. It could not survive without food. It could not escape a collapsing climate. It was immense, but it remained an animal, held inside the same laws that hold every animal. That tension is what makes sauropods so compelling. They were both ordinary and impossible. Ordinary because they fed, grew, nested, moved, and died. Impossible because the scale at which they did those things has no living equivalent on land. The mind has to move between those truths without losing either one. A titan standing beside a river is not a monster waiting for a scene. It is a herbivore choosing where to place its feet. It is a digestive system wrapped in muscle and bone.
It is a breathing machine with air spaces reaching into the skeleton. It is apparent only in the broad sense that it leaves eggs to the future. It is prey when young, difficult when grown, vulnerable when the world turns against it.
The title, The Age of Giants, can make the animal sound like a dynasty. But there were no crowns in the Mesozoic, no rulers in the human sense. Dominance was ecological. It meant occupying large herbivore roles across landscapes, converting plant matter into bodies, shaping habitats by feeding and movement, and persisting through immense spans of time. Sauropods did that better than any other land animals in Earth's history. From the Jurassic into the Cretaceous, they became one of the great solutions to herbivory. Not the only solution. Ornithischian dinosaurs had their own successes, from stegosaurs and ankylosaurs to hadrosaurs and ceratopsians. But the sauropod solution reached higher and heavier. Hadrosaurs later became dominant in many northern Cretaceous ecosystems with sophisticated chewing systems and dental batteries. Ceratopsians evolved powerful jaws and horns. Ankylosaurs carried armor close to the ground. Sauropods followed another path. Small heads, long necks, large guts, columnar support, rapid growth, and eggs. Different herbivore designs can succeed under different conditions. The Mesozoic did not have one answer to plant eating. It had many. Sauropods are the largest answer, but their size should not hide the diversity around them. In a late Cretaceous landscape, a titanosaur might share the broader world with hadrosaur-like herbivores in some regions, armored dinosaurs in others, small mammals underfoot, birds in the trees, pterosaurs over water, and predators adapted to local prey. The dinosaur age was never one line of animals. It was a web. The web changed as sea levels rose and fell. In North America, the western interior seaway divided the continent during much of the Cretaceous, shaping habitats and dinosaur distributions. In South America, large river systems and floodplains preserved many titanosaurs. In Europe, islands and archipelagos affected body size and evolution. Geography kept rewriting the rules. Sauropods responded as living populations do. They diversified where conditions allowed. They disappeared where conditions changed or where the record no longer preserves them. They became small on some islands and gigantic in some continental interiors. Their story is not one steady rise followed by one steady fall. Even extinction did not arrive as a slow fading of the sauropod form in every region. Titanosaurs were still present at the end. Their disappearance belongs to the larger collapse of non-avian dinosaur ecosystems. The age of giants did not simply run out of ideas. It was interrupted by catastrophe. That interruption matters because it separates the modern world from a possible one. Without the impact, titanosaurs might have continued longer. They might have diversified in new ways or declined under other pressures. We cannot know. The fossil record gives what happened, not the alternate histories. What happened is that the long-necked giants ended. Their nests stopped being renewed. Their trails no longer crossed wet sediment. Their teeth no longer fell into floodplain mud. Their carcasses no longer fed theropods, because the non-avian theropods were gone too. The ecological machinery of the Mesozoic broke and reassembled without them. Afterward, plants grew over ground where no sauropod feet would pass again. Rivers cut through sediments that already held their bones. Mammals moved through the spaces. Birds carried one branch of dinosaurs into the New World, light enough to survive where giants could not. The absence of sauropods is part of the modern landscape. Forests today grow without long necks reaching into their upper layers. Grasslands spread without titanosaur trails. Riverbanks dry without circular footprints deep enough to hold rainwater for small animals. The world is full of large herbivores, but not that kind.
Sometimes absence is easier to feel in a museum than outside. Under a mounted skeleton, the missing animal becomes visible through the space it occupies. The ribs enclose air. The neck reaches over visitors. The tail draws the eye across the hall. You can walk around the shape of something that no longer exists.
The skeleton is not the animal, but it gives the absence boundaries. It tells you where the shoulder stood, where the hips rose, how far the head was from the heart, how long the tail extended behind. It lets the mind approach the impossible by walking around it. A cast of Patagotitan in a museum hall can make modern architecture look temporary. Steel beams and polished floors surround an animal that lived before the last seas retreated, before humans, before cities, before the ice ages that shaped familiar landscapes. The body is gone, yet the scale remains strong enough to rearrange human thought. And still, the most important evidence may be smaller. A thin eggshell fragment, a line of tooth replacement in a jaw, a microscopic growth pattern, a pore in a vertebra leading to an air chamber, a track edge pushed up by mud. These details keep the giant from becoming only a spectacle. The detail restores the animal. Size alone creates distance. Anatomy, behavior, and ecology bring it closer. The giant becomes not just a number, but a life system. Not just the largest, but one of the most successful experiments ever carried out by evolution on land. Evolution did not plan sauropods. It never plans. It modifies what survives. A slightly longer neck works. A lighter vertebra works. Faster growth works. A larger gut works. Eggs in the right sediment work. Over millions of years, useful traits accumulate until a body appears that seems designed for grandeur, though it was shaped only by survival. The word design is convenient but dangerous. Sauropods were not engineered in advance. Their bodies contain compromises, inherited constraints, and local solutions. The same anatomy that allowed giant size may have limited agility. The same egg-laying strategy that produced many young left those young vulnerable. The same large body that deterred predators required enormous resources. Life at the extreme is always a bargain. Sauropods paid for their size with appetite, growth demands, reproductive risk, heat management, and dependence on productive landscapes. They gained reach, defense, digestive capacity, and ecological power. For a very long time, the bargain held. When it failed completely for them. No small sauropod lineage slipped through the boundary. No dwarf Titanosaur survived into the Paleogene. The entire long-necked branch ended, leaving only its traces and the living birds that preserve dinosaur survival through a different ancestry. This finality gives the bones a different weight. They are not ancestors of anything alive in a direct line. They are remains of a finished experiment. A successful one, measured by duration and diversity, but finished all the same. There is no modern sauropod calf stepping out from behind a tree. No herd moving across a dawn floodplain. No titanosaur nest warming under sediment. The closest we can come is stone, and stone is both enough and not enough. The stone gives us the physical truth. It tells us that the animal was here, that it had dimensions, that its bones grew and broke and healed, that its feet met mud, that its eggs had shells, that its teeth were replaced, that its body entered sediment after death. It does not give us the animal's inner life. It does not give us the color of the skin with certainty, or the exact sound of the call, or the feeling of the ground under its foot. That missing part is where careful imagination belongs. Not fantasy that ignores evidence, but imagination held close to rock. The kind that looks at a trackway and sees movement, looks at a nest and sees vulnerability, looks at a femur and sees weight, looks at a vertebra and sees air inside bone. This is what makes sauropods and titanosaurs endure in the mind. They are not only large, they are comprehensible piece by piece and overwhelming as a whole. A tooth can be held in a hand. A skeleton can fill a hall. A footprint can collect rainwater. A lineage can span more time than human thought comfortably holds. The age of giants begins with anatomical details and ends with geological scale. It asks how a head can stay small while a body becomes enormous. How a neck can stretch without collapsing. How an egg can produce a creature that will outweigh a herd of modern animals. How a river can bury enough evidence for us to know any of this. The answer is not a single miracle. It is deep time. Many generations. Many failures. Many local successes. A body plan refined and altered across continents. Ecosystems productive enough to support it. Catastrophes severe enough to redirect it. Fossilization rare enough that every surviving piece matters. To look at a sauropod is to see life using time as a tool. No individual animal lived for millions of years, but the lineage did. No single generation invented the giant body, but countless generations carried it. The result was a kind of scale that belongs not just to biology, but to duration. Duration is easy to say and difficult to feel. The Jurassic alone lasted tens of millions of years. The Cretaceous lasted longer still. Sauropods rose, spread, changed, and persisted through intervals that would swallow all of human history without a visible ripple. The bones in a quarry are brief survivors from that immensity. Return one last time to the mud. A river has dropped its water after rain, leaving a low bank exposed under a warm sky. Ferns lean over the edge. Insects move among wet stems. Somewhere in the distance, a conifer trunk creaks in the heat. The ground is soft enough to receive a foot. The animal steps down. Weight spreads through the pad. Mud rises along the sides. The toes press forward. For a moment, the shape exists only as pressure. Then the foot lifts, and water seeps into the hollow. The body moves on, already needing the next mouthful of green. The track remains, not because the animal meant to leave it, and not because the world meant to preserve it. It remains because sediment, water, burial, and time happened to agree. Long after the skin decayed, long after the bones scattered, long after the river changed course, the footprint held the memory of weight. Later, stone covered it. Later still, stone opened again. A human hand brushed dust from the surface, and the age of giants returned in the shape of a step. The sauropod itself is gone. The titanosaurs are gone. The forests that fed them are gone, but the ground still keeps their passage. And in that passage, the largest animals ever to walk on land are not only imagined, they are measured, traced, and quietly present in stone. Around that stone surface, the modern world continues without noticing. Wind moves over the exposure. Rain darkens the print and then dries from it. Lichens may gather at the edge. A boot stops beside it, careful not to step too close. The mark is no longer mud, but it still asks to be read as movement. A fossil footprint has no face, and that is part of its power. It does not show the animal as a restored painting does. It does not give the curve of the neck or the shape of the eye. It gives contact. One moment when a living body and a soft earth met each other, and the earth kept the pressure. Bones tell us what the animal was built from. Tracks tell us that the body crossed a place. Eggs tell us that the lineage renewed itself. Teeth tell us how feeding war against the world. Sediment tells us what kind of landscape held the evidence long enough for us to find it. Together, they form a creature that can never be complete and yet is no longer lost. The sauropods and titanosaurs remain partial, but their partial evidence is vast. It reaches from Triassic ancestors to Jurassic floodplains to Cretaceous nesting grounds, from museum halls to cliffs in Patagonia, from a single tooth to a skeleton that fills the view. Somewhere, still buried, there may be a larger bone than any yet found. Or there may not be. The known giants may already stand close to the true limit. The answer waits under sediment, or it has already been eroded away, or it lies in a drawer under a label written decades ago. Paleontology is full of discoveries that were present before anyone knew how to see them. That uncertainty keeps the age of giants open. Not open in the sense that anything can be claimed, but open in the way good evidence keeps inviting better questions. How fast did the largest titanosaurs grow? How far did they move? How did their necks behave in life? How did juveniles survive? How did ecosystems carry so much herbivore mass for so long? Some answers will come from spectacular finds. Others will come from patient work on ordinary fragments. A new nesting horizon. A better dated ash layer. A more complete skull. A trackway mapped before erosion destroys it. A bone thin sectioned under a microscope. The giants are studied at every scale because every scale holds part of the animal. The largest land animals in history are therefore not locked in the past as simple marvels. They remain active in science. Each new measurement adjusts the outline. Each revised estimate sharpens the range. Each quarry adds a place, a climate, a community, a death, a burial. The giants still change, not in life, but in understanding. And after all the measurements, the image returns to the ground. A broad foot pressed into mud. A river nearby. Plants without flowers along the bank. A body moving away, immense and unaware of the mark behind it. The step cools, dries, fills, hardens, and waits. Long after the animal is gone, the footprint remains a simple fact. Something very large passed here. It stood on the same earth, under a different sky, in a world of conifers and floodwater and heat. The age of giants is not only above us in mounted skeletons, it is below us in the surfaces where weight became stone.